Good morning or good evening, wherever you might be. These days, I tend to meet with people right across the world and they're in different time zones. So today I want to start a discussion about how data fusion is going to be a part of our future. This is just a slight outline of what it looks like. And hopefully at the end of the day, you can enjoy a little bit of this weather. It's a picture we took from the beach last week. And I wish
you make us feel good in Boston, I understand.
That you can enjoy a little bit of it.
Okay.
So data fusion, what is it? It's not a big deal, actually. It's just a stitching of multiple data or information sources into a comprehensive whole with the aim that you have something that has capacity to answer questions that you would ordinarily not be able to address with the component data sources. I use data fusion here in a very general sense to, subsume the idea of fusion at the level of study design, data collection and integration, or even, fusing of estimators. It's receiving a lot of attention all of a sudden, especially in the context of transportability and generalizability. However, data fusion is common and old. It has a long-standing tradition in many fields, including ours. You just think about the human senses, that we are always integrating pieces of information from what we smell, touch, see, hear, to be able to make sense of our environment, to form a more holistic view of things happening around us. In fact, you could argue that prepared food is fusion. I know there are specific recipes that have fusion in the title, but when you have a sandwich, you're fusing different things together and enjoying them. The idea being that you would enjoy the sandwich better than you would enjoy the individual ingredients consumed separately. You see this in computer science. They do this all the time. It's teaching all the Google Street View and AI. In astronomy, the pictures and the images that return from that the Hubble telescope takes, they have to be stitched together to, have a more complete view than you would if you were actually looking at them. If you looked at the individual files before NASA stitches them together, you would be baffled at what you're looking at. But, even standardization in demography, in epidemiology, in the actuaries, these have all involved combining different data sources to come up with an answer to something that they've been looking for. Study design, as we know it, like case control studies, they actually exercises in fusing different data sources to actually answer questions that will be difficult to address without creating such a thing. In fact, if you think about multi-level cohort studies that have environmental scans added to them, geographic information and neighborhood information, measuring these things and adding them to existing cohorts, that's an exercise in actually integrating different pieces of information, of data, to be able to address something larger than you would if you use only the cohort data without the environmental data. And when you see this in the estimation stage too, synthetic controls known to those who do econometrics, for example, the two-sample instrumental variable method, the transport formula, the Frondor formula, in fact, the G formula, are all examples of fusion in action. For example, think about transportability, which you see a lot of work from UCLA and from Harvard and others around the country. When you think about, say, to be able to address what will be the effect of, say, treatment in a target population indexed by S=0, and you would need two pieces of information. You need information from the study sample, say a randomized trial. You need information from the target population. You would take this together and you would try to put them together to be able to answer the question. So for example, what would be the average potential outcome under intervening to set X to little x in that target population will be given by a fusion formula like this. That is sometimes called the transfer formula. This bit here, which you take from when taken from a trial, is simply this by design. Because we've done an intervention and we have a trial over there. The Z just indexing the differences between our study and the target. And that's what we're using to now put together here from the study, here from the target population, to come up with an answer about what things would look like had we done that experiment or treatment in the target population. So this is known to those who are doing transferability, that they are fusing information from two different places at least. And it can involve much more than just two different places, but let's just stick with a simple example. But when we consider, say, a G formula, we do the same thing. When we're interested in, say, what a potential outcome on the treatment will be among those who are not treated, for example, assuming X equals 0 is those who are untreated, we'll be taking information from those who are treated, the outcome, the L specific outcome among those who are actually treated, and combine it with the L distribution among those who are untreated to be able to come up with this potential outcome, which is not directly observed in one specific data set, in one specific subgroup of that data set that we have. We have to combine different parts of the data set to come up with this answer. And this goes on for all these other potential outcomes. And what we see is this happens when what we want to do is not what we see in the target population. We're forced to combine information, to fuse data, to fuse estimators. Now, if we do need fusion to deal with internal and external validity issues about whether the effect was identified in our study and whether we can take the result to another target population, which may subsume our study or not, in which case we're thinking of generalizability, then it follows, in my mind, that dealing with threats to those, the validity would require that we also address data fusion, that we embrace data fusion. Quantitative bias analysis is just one way in which we try to address how sensitive those study results might be to violations of those identifiability conditions. In fact, you could argue that the bias parameters that you use in quantitative bias analysis represent external data, which we can fuse with our study data, where these external data could come from validation studies, existing surveys, existing cohorts, data from your friend who is halfway across the world. I often say you call up your friend in Japan and say, have you got these that I could use to query how sensitive my results might be to violations of the assumptions I'm using to actually claim that I am able to identify effects. So, and typically quantitative bias analysis will involve in a fuller sense probabilistic analysis that uses simulations. This is just a slight detour to mention that simulations have now come to become a thing for us, something we embrace in trying to stitch together various data sources under very strong assumptions about the data generating process, about the questions we want to address. You see this in agent-based modeling. You see it in the various adaptations of these ideas from system science modeling. You see it in the implementation of the G formula, which came from this department, and you've done a lot of work in this area. You can use this to do much more than you would if you just had one data set. This would allow you to do what-if analysis. In fact, what-if analysis would often involve simulations, if for nothing, just to be able to introduce the uncertainty we have about various aspects of the data generating process or the quantities that we're using. But simulations are also used in quantitative bias analysis. It is something that is there and has been a part of it. And I'm sure that, I don't know if Tyler is on, but Tyler will argue that people have difficulty dealing with these things because they're very complicated things, but they have always been there. And if we do data fusion all the time, and we do simulations all the time, and it makes sense that these two things come together. And in fact, they have been together. All I'm doing is trying to show you how they've been together and will continue to be together, and how the idea of being able to embrace data fusion as a framework for addressing the typical tasks that we conduct, that we undertake under causal inference or other epidemiologic inquiries would be something that is fruitful, especially one that would actually require simulations in order to do it well. So we all know in epidemiology that the standard concerns we have about sources of systematic error. In fact, when we're dealing with very large data sets, like many people do have these days, large data, big data, whatever you want to call it, we have data sets that include 20 million observations and all those sort of things. Sampling variation, random sampling variation isn't our concern as much as systematic variation due to other signals that are co-mingling with what we want. In fact, these other sources of bias tend to violate the very things that we call upon in order to claim that we have identification. They would make it hard for us to defend the conditional exchangeability, consistency, or positivity. Unfortunately, these things are often neglected in big studies, and I'm sure that we can have a conversation about why these things are often neglected. So we are magicians. Let's say for a simple case that this is what we actually want, the sort of data we would love to have, but we don't have it. And we have this. We don't have the column U, the variable U, a confounder that is completely unobserved, the true properly measured X isn't there, the treatment. We have a version of it that is possibly misclassified, and we have the outcome, and we have it for some people. So what you have here is a lot of missing data. And somehow we're supposed to be able to answer a question that we wanted to answer with this, with only this partial view. That's the call on it. So consider, for example, this simple DAG, directed acyclic graph, where X is our treatment, Y is the outcome, C is a measured confounder, U will be some unmeasured confounder, and the true data generating process is such that we have, say, a risk difference when C is, say, set to a reference, say 0, for the effect of X on Y, the conditional risk difference being a 0.05, for example. And this is what it looks like. And then consider that we don't have the U, and U is unobserved. We basically end up fitting a model, for example, a conditional model for Y given X and C, and we end up having these parameters that come out of it. And we would try, when we try to interpret an estimate of this phi X as something that should have been alpha X, we're going to be find misleading results. For example, this is what it should have been, 0.05, but we'll find that it's 0.079. So the biased model basically gives us an answer that has several problems. One, the coefficient of X is off. The coefficient of C is also off. And so this uncontrolled confounder U isn't just bad news for X, it is bad news for a lot of things. So what we've talked about here is what it does is that when we don't adjust for U, we have uncontrolled confounding of the effects of X and Y. We saw that in the coefficient of X being off. We also have a collider stratification bias in the association of C and Y. That is, in this case, it was a small quantity where this thing here is no longer, this here is not a good estimate of that. It's not consistent for it because if you went back to the DAG, you will see that in the absence of U, this U being measured, we have this backdoor open. Then the coefficient or the association between C and Y will now involve not just this direct path here, C to Y, but this one, C, going through X, because we condition on X. This is a collider here, going through X, coming through U to Y. This is collider stratification bias in action for C. So this will be the reason why you would have a concern for the table 2 fallacy. Good luck trying to interpret the coefficients of all these other measured covariates as being anything meaningful when you already have a control confounding of your target treatment effect. There's also the risk of amplification of the confounding we have in X and Y if some of the C's were included in the measured confounders or covariates that we're using to adjust for confounding include instrumental variables. That is, variables that are only associated with X in this case, but perhaps not with C or U, and would affect Y only through X. So such instruments which may find their way in doing our selection of the variables in C might actually then amplify the bias due to U. So it can be a serious problem. So quantitative bias analysis then tries to address these things by looking at how sensitive the result sensitivity is to uncontrolled confounding, measurement error, selection bias, or a combination of these. Like I said, when we have very large data sets and we're analyzing this one large data set, our problem, our concern, I argue, will be about these other things that are going on, effects that are mixing, variables that are misclassified or information bias due to measurement error, selection bias, samples that are being lost at rates or subpopulations at rates that have information about the outcome and the effect of the treatment. Bias formulas, for example, have now been developed to use for external adjustment, missing data methods that we integrate these data on the omission confounder with the record level data. And of course, we shouldn't forget there's a very popular branch of this that involves doing bounding analysis, but I will not be talking about that today. So some of these formulas have been published in the literature and have been around. The thing is that for every type of effect measure that you find, you would need a different formula to deal with the issue, to adjust for possible uncontrolled confounding. This one with Tyler on generalizing the previous paper. This one taking a review of what the literature looked like at the time and introducing a general framework for actually simulating the bias that we can actually use in our studies. So talk a bit about some of those things here. So for example, those bias formulas, what do they look like? They basically are solutions to the difference between our unadjusted or the U unadjusted estimate and the one that actually does adjust for it, that quantity. That difference, of course, is the bias. The expression that you solve and get that is the bias formula. The estimate that comes out of plugging in values to solve for this will give you a bias factor on this side. These quantities here represent what we call the bias parameters. These bias parameters, or these quantities here, would have to come from outside the data. What do they represent at an intuitive level? These bias formulas try to capture through these expressions this association, this backdoor through that involves U. A backdoor is simply this undirected path that begins with an arrow pointing to X, connecting X to Y through some unmeasured variable, in this case U here. So this backdoor path is open. The bias formulas try to capture what it would look like if we took a journey from X, conditional on C, and walk towards U, and pass U and get to Y. So it will quantify this and quantify this, The idea being that if we can we'll get an estimate of how big this backdoor is, we can remove it, we can block it. That's what the formula does at the intuitive level. At the core of all these analysis, what we see is that they involve integration of various pieces of information. One, for example, the bias formulas look like this, is that they try to get information on how the supposed U is related to Y and plugs it into that expression, and also gets information about how the U is related to X and C. The key thing being how it is related to X in the presence of C. The same thing here, how U is related to Y in the presence of X and C. A different way to look about this one involves two pieces of information integrated through a bias formula, is to use a singular expression, but this singular expression requires that you have information jointly on how U is related to Y and X conditional on C, which can come from a validation study, can come with internal or external, or come from a survey that exists out there, or information in the literature. I get it, it's hard to think, to specify these things, but I'll talk about how you can actually think about personalizing some of these things. The idea is, if you can get an expression for how U is related to the outcome and the exposure or treatment conditional on C, you can use it to reconstruct as a function of these observed data, because you have data on Y, you have data on X, we have data on our measure confounders, to reconstruct this distribution. So to create the distribution we would have had under the assumed connections between U and Y and U and X given C. Once we have this reconstructed or fused distribution, we can analyze it the way we would analyze any other data, the way we would have analyzed just the observed data. Only this time we have U. And if we change our minds about how that U is related to Y or X and we want to vary it, we don't have to redo the whole thing. Once programmed is programmed. What you have to do is change the parameters, join in that specify how this is related. So there are various examples of how you would actually just use data fusion to address uncontrolled confounding, the bias offset, which is in the back of the slides. The one I mentioned briefly is the one we just talked about, the weighting and imputation, and the simulated bias offset. The weighting one is the thing I just talked about, which is their aim is to recreate U-specific tables of this joint distribution of that we would have observed had U been measured by using a function of U given Y, X, and C, our observed data, and use it to reweight or to recreate U within this data set. This, for example, imagine that we have these data, and this is within some level of C or conditional on C. This is what we would have had if we had a binary U specific tables would have looked like, but we don't have these two U specific tables because we would have been able to conduct our analysis conditional on U using this. We actually have this collapse table that is collapsed over the U. Our aim is to try to impute what each table will look like by recreating using an expression that looks like this, which, for example, we would generate, say U were binary and we had a length function here, where was based on what we have from our external data, we will be able to capture this series of lambdas that would actually connect and reconstruct the joint data between involving U, showing how U is related to X and Y and in whatever functional forms that we can find from the external data. Conditional on C. Now, we can leave out the parameters that are indexed by lambda C by not specifying them if it's huge, large, and we don't want to deal with that. But we must specify these other lambdas, the ones involving the treatment and the outcome, and the values that they would have attained conditional on C. That's key. The idea being that if you do that, all you're correcting for when you use so generated will be the coefficients of X in the final model in which you regress Y on X on C and U. The coefficients of C will remain unadjusted. However, if you do include the lambda C's, they get to be adjusted as well, the coefficients of C. So the idea is to take this crude data, use that weighting scheme, or it can even be implemented as a simulation to simulate the U, to create U-specific data, to recreate the U that would have been observed under those specified relations, lengths. Once we have the U, we can analyze it any way we want. We don't need different formulas for actually using the U. So we can fit conditional models, we can do standardized models, whatever we wanted to do with it. We can do propensity scores, whatever that is. Once you have the U, you can implement whatever your final model will look like. So for example, we use this in a study on the association between obesity and chronic kidney disease, where we're worried about inflammation being something that is not observed in the kinds of data sets we're working with, very large data sets, and we were able to use this type of approach to adjust for the association between, or the various associations between several outcomes in chronic kidney disease. We looked at all-cause mortality, cardiovascular mortality, cancer mortality. We have this thing here that used like a reverse J, and when we accounted for various forms, what we call weak confounding, moderate confounding, and strong confounding, we saw that it did move this at the higher levels of obesity. It did affect some of the associations between, say, obesity and all-cause mortality, or cardiovascular mortality, or cancer mortality. So we were able to just implement this, and once we've created this inflammation or any such U index in this data set, we could use it to analyze all these other outcomes. We can even vary how the U, or inflammation in this case, is related to each of the outcomes, while maintaining the association between the U and the X, obesity in this case. Now, consider this example where we can simulate the bias. So we often will begin our studies, well, some of us do, in specifying some directed acyclic graph that we think governs the data generating process for our study. So for this one, this setting where we know that this is what we take as our data generating process, it is possible for us to think about how much bias that you would be responsible for under the assumed associations or the effects of U on X and Y in the presence of C. So what we do is we specify this U, simulate it, whatever distribution that is, that we're assuming that we have, the marginal distribution for it, use that information to generate the DAG that we might have observed involving U, had we had U. What I found is, in our work and with my students, is that we found that it's easier for us to imagine how U might affect X than to reason about it in the reverse direction. which is what you do in a bias formula. Now, so you specify how you, in this case, with seeing you as being having a causal effect on X and having a causal effect on Y. But it doesn't have to have a causal effect on both. It just needs to have it with one of them at least. And the other one could just be an association, that she is an unknown common cause, or a combination of having a direct effect or indirect effect, as well as sharing an unknown common. Whatever you think that is, if you were to generate it, how it would be under the null effect of X on Y. It then follows that when you do regress Y, for example, on X, adjusting for C in whatever way you want to adjust for it through IPTW or whatever, that if you find the link between X and Y, it will be due to the unobserved U, the U that you just left out. If you can get this quantity, you can use this quantity to offset bias in your study. So don't read this. This is just a step read about a possible implementation of this. You can read it from the paper. This is an example of where we actually implemented this. We try to look at how the effects of electromagnetic field exposures on childhood leukemia will be due to uncontrolled confinement by residential mobility. We were able to use this data from California, the California Power Line study, and we were able to recreate the residential mobility that we think we would have seen with partial information we had from a subset of the study, and then simulated how much residential mobility under the assumed links would lead to possible effects, a possible association between EMF and childhood leukemia, when in fact, EMF doesn't have an effect on childhood leukemia. When we assume that it doesn't have an effect on childhood leukemia, we could see various magnitudes of what this bias will look like. And we were able to then use the generated bias due to this residential mobility to actually offset our the possible bias in our California Power Line study. This is simplified DAG representing various theoretical models in the field about how mobility and will be related to EMF exposures and leukemia. And when we did that, we were able to sort of offset this and see to what extent our results were sensitive to the possibility, to the fact that we didn't have residual mobility measured on all the study participants. So the idea here is what I've done, and we can have a discussion. I do have some extra slides, is that data fusion has always been a part of epidemiology, statistics, causal inference, engineering, biology, genetics, the omics, informatics, and many, many fields, astronomy. The idea that they have one data set that contains everything they need to be able to address the questions they want to address, substantive questions, is something that is strange to a lot of fields. So they are in the business of always stitching together information from various areas to be able to answer questions. I'm arguing that using data fusion, the idea of stitching together various data, and some of these data may come to us as equations that we can convert to data. Simulations will allow us to convert those equations to the kinds of data that would have given rise to those equations, which we can then use to augment our actual data. That this is a very useful way of reasoning about the things that go wrong in causal inference. And that is, we make a lot of assumptions, some of which are untestable, about identification. And the reasonable thing to do will be to step back and say, we know that many of these things are typically violated. How bad do things have to be before our results can be turned over? And I believe that quantitative bias analysis is going to be really critical for those of us who are involved in using very large data. We're going to have to formalize the idea and normalize the idea that we have to fuse data, external data to our study data, and those external data can come in various forms, and the analysis can proceed using simulations and more and to get a fuller picture. The idea is hopefully that we're able to get this. Another picture of just a few days ago in California, to sort of broaden our horizon, make causal inference more credible and relevant. Use it to fuse not just designs, which we're used to, but fuse data and the estimators we use for getting at whatever our target estimates are, but to actually integrate theories and knowledge across disciplines. All right, thank you.